In previous videos, we've looked a little bit at the support system, the head and spine, and how the muscles of the back work in conjunction with these components to produce effortless upright support. I want to say a little bit more today about the spine itself. The spine is a flexible vertical column made up of really more than over 33 vertebrae, but many of them are fused together around the sacrum and tailbone or coccyx. And we can only really find individual vertebra from the neck down to the lumbar region. So there are actually 24 movable vertebrae, and then the vertebrae that form the sacrum and coccyx are fused together. And all those together make up the spine. If you look at the spine in more detail, you could see that it's got the four curves. We're familiar with the cervical curve, kind of if you look at it from this side, inward here, and the lumbar curve. And then we have the broad thoracic curve, kind of, again, if you look at it from the outside here, from the back, it's the broad thoracic curve, and then the fourth sacral curve. And those four curves make up what we know as the human-shaped spine. Many of us are familiar with the notion of a plumb line and the spine that sort of curves around the plumb line. It's given that's sort of an anatomical concept. You'll see anatomical charts that depict the spine as this vertical, kind of curvy vertical column. Very misleading, because it implies that to create the human being, you have these vertebrae that have been stacked one on top of the other, maybe forming a curve, but they're stacked kind of vertically in such a way that we can now support upright posture by having muscles on both sides that keep the whole thing from falling over. And it actually, in fact, the human spine did not evolve that way. If you think about a fish going through the water, of course it has a spine, and it's oriented horizontally. To come onto land, which some of the fishes did to become amphibians, the spine, which is rather undifferentiated in a fish, begins to form a little bit of a bridge between the fore and hind limbs, because now you've got an animal moving on land with these limbs in the front and back, and the spine has to form a bridge between the two. And it's rather undifferentiated in these early, amphibians and reptiles. When you get to the mammals, then you begin to see a more recognizable or definable broad thoracic bridge that the spine forms between the fore and hind limbs. And now you can understand a little more of how the spine begins to form these curves, because with that broad thoracic curve forming a bridge between the fore and hind limbs, you also have the head pointing down, so you need a compensating curve, what would be the cervical curve, to support the head. You also have parts of the spine that support the back legs, becomes the sacral region, and you have a clear tail. So now you have these clearly defined regions of cervical, thoracic, lumbar, sacral, and tail regions. When that animal comes more fully upright, as it did in many of the primates, now that horizontal and curved structure becomes more of a angled upward, or in the case of humans, perfectly vertical structure. And now you see a clear lumbar, thoracic, cervical, thoracic, lumbar, and sacral curves that define the human spine. Now, there are two things that we can glean from this that are really important. One is that because we're no longer talking about creating something mechanically that just sort of stacks vertically, but something that came up from horizontal to the upright, we're talking about a system that's naturally biased, which is why the muscles in back, which are maintaining the support of the trunk, are very, very different than the structures in front, which in a four-footed animal would hang down, and even in humans, tend to create a weight in front. So we have these really important groups of muscle on the back that are key to our upright posture. The second thing is that in order to come upright like this and to become a fully upright structure, it's no longer possible to have a broad thoracic curve without a lumbar curve to compensate. Otherwise, the whole thing is falling forward. And we could kind of see that if you see a dog or a cat standing on their hind limbs. They can do that, and sometimes they become quite adept at balancing on 2 feet, but they're not designed for that because there's too much weight in front. We have the broad thoracic curve that gets more gentle, and then a compensating lumbar curve supporting upright posture. This brings us back to the question of how the spine functions as part of the upright support system. One of the clues is the intervertebral discs between the bony column of the vertebra, which we could see in the illustration. If the spine were nothing other than a weight-bearing device, and it is partly a weight-bearing device because you have the head stacked on top, and then you have the entire trunk, which has a lot of weight that is connected to the pelvis and sitting on the tops of your femurs, the heads of the femurs or your thigh bones. If the spine were nothing but a weight-bearing device, everything would be pressured downward and the whole spine would be compressed. But that's not in fact what happens in a healthy spine. Particularly if you look at young children, you could see that the spine seems to be very elongated. That's partly because young children have a straighter spine. That's part of development. But it's not just that. They also have a lightness that enables those intervertebral discs, which contain a lot of moisture, to act as hydraulic mechanisms that help to maintain the length of the spine. The same is true with the musculature, which doesn't simply pull on the spine or hold it up, but works in conjunction with the spine so that the two things together form a dynamic architectural structure, sometimes called a tensegrity structure, that actually produces a combination of forces between the bones that keep the muscles lengthened and the muscles that act on the bones to produce upright support in the spine itself with a minimum of effort, so that the muscles and connective tissues and bones together make a lengthening structure that helps to maintain upright support. So the spine in humans actually becomes a vertical lengthening device for helping to maintain upright posture. So this brings us back full circle to the question of how the head balancing on top of the spine, remember that it's weighted forward, and the spine itself, which helps to space apart the connective tissues and muscles, how those elements work in conjunction with the connective tissues and muscles to produce upright support with a minimum of effort. And one of the things that we also can glean from this is that in order for the spine to be healthy, it has to maintain length, because to the extent that muscles and connective tissues begin overworking, and this is also true if they're underworking and we're slumping, to the extent that that happens, the spine will get compressed, and that's a sign of a spine that's not healthy. So in order for the spine to be healthy, it has to maintain length. Length is a key attribute or feature of the spine which maintains its health over time.